Hi, welcome to lesson 7.4 about limiting reactants. We're going to take notes in the packet, but also have a blank sheet of paper as well. So first, what is a limiting reactant? When you think about how you're going to make a sandwich, and you kind of saw this in the virtual lab, maybe you use like 2 slices of bread, 4 slices of turkey, and 2 slices of cheese. So let's say that you had 15 slices of bread, 12 slices of turkey, and 4 slices of cheese. How many sandwiches could you make? Well, based upon these values, we could make 7 sandwiches from the bread, we can make 3 sandwiches from the turkey, and we can make 2 sandwiches from the cheese. So based upon that, we could really only make 2 full sandwiches because the cheese is limiting how many total sandwiches we can make. And the same concept applies to our chemical reactions. A limiting reactant is the reactant that's used up first. So all of it is completely used. There's none left over on the reactant side. It's all turned into products. Once it's used up, the reaction completely stops. It produces the smaller amount of product. So today we're going to do a few calculations and you're going to see more than one amount of product that could be produced, but because of the limiting reactant, we can only produce as much as that limiting reactant allows. Like if we look back at the sandwiches, we had enough bread for 7 and enough turkey for 3, but we could only make 2 full sandwiches because of the cheese. And the same will apply to our reactions. So it produces the smaller amount of product. In comparison, we have our excess reactants, the reactant that is not completely used up. There's going to be some of this reactant left over that hasn't done anything. It still stays exactly the same. And it produces the larger amount of product. So how do we solve these limiting reactant problems? First, we're going to do our stoichiometry calculations for each reactant to the exact same product. Sometimes the product is told to us, and sometimes you'll just choose one that makes a little more sense. The reactant that produced the least amount of product is the limiting reactant. So we're going to look back at the reactant. The limiting reactant determines the maximum amount of product formed, which is also called the theoretical yield. The reactant that produced the most product is called the excess reactant, and there will be some of it left over after the reaction stops. So let's try a few problems. What mass of hydrochloric acid is formed when 3.5 grams of hydrogen reacts with 15.1 grams of chlorine? First, we need a balanced reaction. So from left to right, we have 1, 1, 2. We're going to make 2 stoichiometry setups. So I'm starting with 3.5 grams of hydrogen, as well as 15.1 grams of chlorine. So first for my hydrogen, I'm going to cancel out my grams diagonally, and on the other side would be 1 mole. In 1 mole of hydrogen is 2.02 grams because there's 2 atoms. Next, I'm going to use my mole ratio. So I'm going to look at the balanced reaction. There's 1 mole of hydrogen, and we're trying to figure out how much hydrochloric acid can be produced. So when we look at the balanced reaction, there's 2. And it asked about grams or mass, so we're going to turn that into grams. 1 mole of HCl. We'll go ahead and add 1 hydrogen and 1 chlorine for a mass of 36.46. So calculating from left to right, starting with that 3.5, dividing by the 2.02, multiply by 2, and multiply by 36.46. Rounding to 3 sig figs, this would be 126 grams of hydrochloric acid. Take a moment, pause the video, and try the next setup on your own. Okay, for the next one, we're going to do a similar setup. We have 1 mole of the Cl2. So I have 2 chlorines at 35.45 each for a mass of 70.9 grams. Then I'm going to do the mole ratio, but this time with this Cl2. When I look at the balanced reaction, there's 1. Turning it into the same exact product, so I'm going to turn it into the HCl. You'll notice that these last 3 boxes are going to look exactly like the setup from above. So I'm just kind of copying that. When I calculate from left to right, my final answer should also have 3 sig figs. So 15.1 divided by 70.9 times 2 and times 36.46 for a final answer of 15.5 grams of HCl. So this time we have 2 setups. We're going to compare these 2 values and look for the one that's smaller. So the 15.5 is obviously a lot smaller than 126 grams. So that's the amount of HCl that will be produced. 15.5 grams. But then the question is asking the limiting reactant. So I'm just going to look to the left in this setup, and that came from the Cl2. So that's my limiting reactant. The one that produces more is going to be the excess reactant. So that was the H2. Now, what we're going to add on a separate sheet of paper is figuring out how much of the excess is left over. And we're going to use these amounts. So how many grams of excess reactant are left over? We just determined that the excess reactant is hydrogen. I'm also going to use those values. 126 grams of the HCl and 15.5. Now, the 15.5 was produced because that's the lesser amount. I'm just going to start by subtracting those values, and that's going to tell us how much wasn't made. The units for that, though, are of the grams of HCl, and I want to know how much of the H is left over. So I'm going to go ahead and work backward using the same balanced reaction. So I have 1 mole of HCl. If I look back at my previous work, the mass of HCl is 36.46 grams. Then I'm going to use my mole ratio to turn the moles of HCl back into H2. I'll look at the balanced reaction. There's 1 H2 and 2 HCl's. Then I'm going to use the molar mass of hydrogen to turn it into grams. I'll calculate this. I'm starting with 4 sig figs over on the left, so I'll keep it as 4 sig figs. So the 110.5 divided by 36.46 divided by 2 and times 2.02. So that there's 3.061 grams of the H2, or that excess reactant, that are left over. That means that about 3 grams of the hydrogen did not react at all, and just the hydrogen is left over. All of the chlorine was used up. Now, we can also figure out how many grams of that hydrogen were used up. We could do this in 2 ways. So we just calculated that 3.061 grams were left. If we look back at the original equation, we started with 3.5 grams of hydrogen. So we could simply just subtract that. 3.5 minus that 3.061, and there's 0.439 grams of hydrogen that were used in the reaction, which is really, really small. Like, we didn't use much of the hydrogen because the chlorine limited it so much. Let's try another one. How many moles of CO2 are formed when 27.8 grams of oxygen reacts with 15.7 grams of methane? We're going to do this in the exact same way. So I have my balanced reaction here, 1, 2, 1, 2. Starting with the 27.8 grams of oxygen, as well as the 15.7 grams of the methane. First, I'm going to turn my grams of the oxygen into moles of oxygen. There's 2 of them, so 32 grams. Next, I'll look at my mole ratio. There's 2 moles of oxygen and we're trying to figure out how many moles of CO2 that is. So from the balanced reaction, 1 mole of CO2. I don't need to turn this into grams because the question is just asking about moles. I'm going to do a very similar process for the CH4. 1 mole of CH4. We have 12.01 from the carbon and then 4 hydrogens for a mass of 16.05. Then I'll use a mole ratio. I have 1 mole of carbon dioxide again and 1 mole of the methane. I'll start by calculating the top one, 27.8 divided by 32, also divide by 2. I'm going to keep 3 sig figs for 0.434 moles of CO2. For the bottom, 15.7 divided by 16.05. And then the ones don't really change anything, so that's going to come out to 0.978 moles of CO2. Once again, I'm going to compare these values, and the smaller amount is the one that's actually made. So 0.434 moles of CO2 are going to be made. That's coming from the limiting reactant of oxygen. So my other reactant is in excess, which is the CH4. Then I want to figure out how much was used and how much was left over. So I'm going to use these values on the next slide. To figure out how much of that CH4 is left over, if it was just from the CH4, it would have produced 0.978 moles of the CO2. But because there's a limiting reactant, it only produced that 0.434 moles of CO2. So first, I'm going to start by subtracting those values. So the 0.978 minus 0.434. So my starting value for my stoichiometry setup is 0.544 moles of the CO2. I want to get that back to grams of CH4. So I'll first start with my mole ratio of the CO2 to the CH4. If I look back at the balanced reaction, I have 1 CH4 and 1 CO2. Then I want to turn that into grams. So 1 mole of CH4, and I have that value on the previous slide, is 16.05 grams. So 0.544 times that 16.05. I'll round to 3 sig figs for 8.73 grams of CH4. So once the methane and oxygen reacted, there's 8.73 grams of the CH4 that was left over. Now, how much was used up? If we used 8.73 grams, we're going to look at the starting amount of CH4, which was 15.7 grams. And we'll just go ahead and subtract them. Which is 6.97 grams of CH4. Sorry, this was how much was left over. That was what we calculated in that previous slide, leftover. So we used the starting value minus what was left over to figure out what was used up. If you're just working with moles, a quick trick that you can do is take the given moles divided by the coefficient and then just decide which value is larger. But that only works if you're given mole values. So you could use this if you're given mole values. You're going to go ahead and complete practice K and L, the limiting reactant practice that you'll find on Canvas. Scan and upload both sides. At the end of the week, you're going to have quiz number 3, which will be on this limiting reactant, as well as percent yield.